Hello everyone. Today we have another LeetCode problem. Today's LeetCode problem 70, climbing stairs. It's an easy rated problem. It says you are climbing a staircase. It takes n steps to reach the top. Each time you can either climb 1 or 2 steps. And how many distinct ways can you climb to the top? Now it's rated easy, and the code to it is very short. Like, it truly is an easy problem, but it's important to understand this question. So all it's saying is, if we were given a staircase of some length, let's say this has 3 steps, so this is n equals 3. Well, how many distinct ways can you climb the staircase if you can always either take 1 or 2 steps? So we can always take 1, 1, 1, so that's just 1, 1, 1. Or we could also start off with 2, and then we have to take 1. 2 and then 1, or we could start off with 1 and then take 2, so that's 1, 2. So for n equals 3, that would be 3 distinct ways. Okay, pretty simple. But what if I gave you a longer staircase? Let's say n equals 6. Now let's draw this. We would have 1, 2, 3, 4, 5, 6, and if you haven't noticed, every single item in here adds up to 3, because that is the requirement. So we would just create any permutation of 1 and 2 that adds up to 3. So this is equals to 6, and then we could do this. 1, 2, 3, 4. That equals to 6, and we would be doing this for a really long time. Now, what we can actually do instead of all of this is actually, let's use dynamic programming. And what dynamic programming essentially does is, we take this big problem and we break it up into a smaller problem. Now, what do I mean by that? Here, if we are starting here, we have 2 choices. We either take 1 step or we take 2 steps, right? So the 2 different paths that we can have, either start with a 1 or start with a 2. Okay, simple enough. Now, let's say we decide to take this 1. Well, we can think of it as n equals 6, or we can actually just forget that step and start here. And now this is an n equals 5 subproblem, right? And that makes the problem a lot easier, because what ends up happening is this is 1, and we're going to use DP for dynamic programming of 5. Now, if we were to, instead of 1 step, take 2 steps, now we are left with a 4-step subproblem, which is DP of 4. Now, at this point, this is still not solvable. We don't know what DP of 4 is. We don't know what DP of 5 is. So now let's do a n equals 5, which is, let's see, 1, 2, 3, 4, 5. And again, we can either take 1 step, and that becomes a DP of 4 problem, or we could take 2 steps and make it a DP of 3. Okay, now we're getting somewhere. We have solved a DP of 3 before over here, but we don't know what a DP of, DP of 3, sorry, but we don't know what a DP of 4 looks like. So let's do that case right now. DP of 4, which is 4 steps, 1, 2, 3, 4, and we can either have 1 and DP of 3, or 2 and a DP of 2. Now let's just keep going down all the way. So n equals 3. That ends up being 1, 2, 3, which is a 1 and a DP of 2, or a 2 and a DP of 1. And then we could do a DP of 2. Now we can either, this is n equals 2, which is just 2 steps, and this is either a 1 DP of 1 or a 2 steps, and then we have an n equals 1, which is a just 1 step. Now what ends up happening is, if this is DP of 1, it's just 1, we can just build our way up. And this becomes 1, and what is dp of 1 again? It's just 1. 1, 2. Now here, we can go, well, we know what dp of 1 is. That's just 1. Now what is dp of 2? Well, it starts with a 1, and it can either be a 1, 1, or it can start with 1 and be a 2. And we do the exact same thing here. But we don't necessarily we don't need to write each path out. We just need the number of distinct paths. For this one, yes, it is 1. For here, these are actually 2 paths, right? For here, these are 3. So what this means is, for this case right here, dp of 2, we said, breaks off into 2 different paths. So what we could do, what we know is it breaks off into 2. dp of 3 breaks off into 3. So this is 3. So we know that this is 5. And we can use that here. This is 5. And this is, what is 3? 3 is 3. So this would be 8. And finally, for n equals 6, well, dp of 5 breaks off into 8. 1, 2, 3, 4, 5, 6, 7, 8. And dp of 4 breaks off into 5. 1, 2, 3, 4, 5. So that would be 8 plus 5, which is 13. And see, just by going all the way down to n equals 1, we were actually able to go all the way back up to whatever number. So in this example, we just start at the top and then work our way to the bottom, but we could just do is start off at n equals 1. And, well, actually, we're going to set our n equals 1 and our n equals 2 as what we call base cases. These are as simple as a problem gets, so we're going to store those answers in some sort of memory, and from there we're going to build our way to the top until we reach whatever n is, and then output an answer. Now, the important part here to notice is we need to identify something called a reoccurrence relationship, and in this case, that just means what is dp of n equal to? That just means we need a relationship between dp of n and some dp that has a n that is smaller than the original n. What does that really mean? Well, here, when we used n equals 6, we used n equals 5 and n equals 4. Those are both smaller. So we could say that n equals 6 was actually just equal to n equals 5 plus n equals 4, right? Well, we could do the exact same thing here. This is 5 was equal to 4 plus 3, right? Here, 4 was equal to 3 plus 2. So it is very easy to spot the relationship now. All it is dp of n is equal to dp of n minus 1 plus dp of n minus 2. Now, what is dp? dp is that piece of memory that we're going to be using to store these. And what do I mean by base cases for n equals 1 and n equals 2? Base cases here are just what we initialize our memory with. We know that n equals 1 has an answer of 1 and n equals 2 has an answer of 2. And then from there, let's say we want to find n equals 3. Well, we don't even need to look at the pictures anymore. dp of 3 is equal to dp of 2 plus dp of 1. And then we look for dp of 1 and dp of 2 here, and that just gives us 1 plus 2, which means that n equals 3 gives us 3. How about 4? Well, that's just dp of 2 plus dp of 3, which is 5. Okay, how about 5? Well, that's just dp of 3 plus dp of 4, which is 8. So 5 is 8. So what is 6? 6 is just 5 plus 8, which is 13. See, notice that it's always the 2 items before it. And just from that, we were able to take a problem that seemed very complicated with lots of different paths, and we were able to break it up into a very simple dynamic programming solution. And that's just because we rely on the fact that we can easily find the answers to the very simple solutions. Now, here we would start with n equals 1 and n equals 2 and build up all the way to whatever n. We already said that, but that just means that this has a time complexity of O to the n, linear time complexity. And that's just because, well, we're performing O to the 1 operations here, n times, which is just O to the n. Now, let's head up to LeetCode and see if we could code up the solution. Alright, now that we are over in LeetCode, this is very short solution. All we have to do is let's initialize this piece of memory, and let's use a dictionary so we can store keys as well. And we know that the base case of 1 is 1 because there's only one path, and that's to take one step. And for 2, well, you can either take one step plus one step, or you could take 2 steps. Those are the 2 base cases, and that's all we need. Now we can create a for loop which goes from 3, which is the very next case after our base cases, and we want to go all the way to n plus 1, because in this case we would not count n plus 1 and we would just stop at n. And here we include our reoccurrence relationship, which is again tp of I here is equal to dp of I minus 1 plus dp of I minus 2. And we could just return dp of n. Now, a lot of people will actually just have an if statement that says if n is less than or equal to 2, we could just return dp of n. That is completely correct, because if it is less than or equal to 2, then we actually have it in the base cases already, but we don't really need this. We could just shorten the code, because if n was something like 2, or if it was something like 1, it's not an edge case that will break this. This will be a range from 3 to 2, and in Python that doesn't throw an error. That just throws an empty list to iterate through, which is okay, because that means we skip this for loop and go straight to return dpn anyways. So if we did everything correct, we can just check our solution. There you go. Very efficient time. I hope you guys enjoyed this video, and please subscribe if you want to see any more LeetCode solutions. Thank you for watching.